Good morning, everyone. Welcome to another exciting edition of Tech Saturday webinar with Times Pro. We are thrilled to have you join us today as we delve into the exciting world of LLM ops and the career paths that awaits us in this rapidly evolving field. So please join me in welcoming our esteemed speaker today, a true polymath, Rusi Chatterjee, the CTO at Genius Rise. But he isn't your average CTO. He's a programmer, a data scientist, a metal hat, and a math geek. So Rusi brings over 13 years of experience with 11 years in the exciting world of tech startups. He has shipped real-world deep learning solutions, managed massive data sets at petabyte scale, and even built search functionalities for major e-commerce platforms like Practo and Snapdeal. He possesses a strong skill set encompassing front-end, back-end, data engineering, artificial intelligence, machine learning, and even DevOps and management. He's not only technically gifted, but has also led engineering teams of up to 50 people, demonstrating his strong leadership qualities. But his curiosity doesn't stop at the professional realm. When he is not building or leading, he delves into the fascinating world of pure mathematics, exploring complex systems, and even computational neuroscience. So, in today's webinar, Rusi will guide us through how to architect LLM applications, operationalizing LLMs in production, DevOps in LLMs, and also inference optimizations, and many more topics, obviously. So, sit back, relax, and get ready to embark on a journey where Rusi will be guiding us through the intricacies of LLM ops mastery and its career insights. So we can put all our questions in the Q&A box, and we will be taking it up in the end. Over to you, Rusi.
Cool. Thank you for the intro. Okay, so for a very short introduction about myself, hi, I am developer. Right. So one second, I'll just share my screen from my laptop so I can do the presentation. Cool. So I hope it's visible.
It is visible, yes.
Right. Cool. I'll get started off then. Okay, so today we'll be looking at engineering of GenAI. So that includes major part of the engineering of GenAI includes operations. I mean, like a 90% of engineering includes operations. Right? I will be talking about these three major, let's say, topics. Right? One is we will look at very shortly what a model is. Then we will look at what runs a model. What is the runtime stack that we require to run different kinds of AI/ML models. Right? These are not just LLMs. I mean, AI/ML models include a lot of different large model category models as well. Right? So we'll be diving into deep into the stack that runs all of this. And finally, we'll look at operations. So we'll be using the runtime stack in order to do LLM ops with these models. These LLM ops could be either deploying these models for inference or doing fine tuning or doing pre-training if you are lucky enough to experience that, right? So this is the major, let's say, agenda of today's presentation, right? So I'll go right in. So what are models? Okay, I'll also use this laptop. Okay. So models are essentially, models are essentially some kind of an architecture or some kind of a, let's say, a black box wherein you feed in input and you get output. This input is in the form of vectors, outputs are also in the form of vectors, and this is essentially a vector computation graph. Right? So a vector computation graph is nothing but a bunch of vector operations happening to an input and then giving you the output. Right? So what is a model? A model is composed of two things. One is the structure itself of the model, which we call also as the architecture of the model. Usually this is a piece of code, right? So for example, if you're using a transformer model from Hugging Face, the implementation of the model is in the transformers library, right? Similarly, there's an implementation for a forward pass and maybe an implementation for a backward pass. So when you have a model, if you want to do inference, you just do a forward pass through the model. You feed the input data, get the output data, and you're done, right? So the code for doing that. And if you are training a model or fine-tuning a model, you need to do both. You need to do a forward pass, calculate the loss, and do a backward pass. This is basic deep learning, right? So for that, we need, again, the code for doing both the forward and backward passes. And finally, we need some code to do data preprocessing. So all this code makes the structure of a model, right? And the second thing that consists of that the model consists of are the weights, are the trained weights of the model, right? So if I have some code and if I have the weights, then I can load the weights into the code and then I can run the model, right? So before I move on, any doubts over here? If yes, just raise your hands. If not, then we'll just move on.
We have one raise. Yeah,
Go
so
on.
would you like me to allow them to talk or put them the question answer in the chat box?
I mean, question answer is better.
Okay. Swati, you can put your question in the Q&A box.
Okay, cool. So let's move on to the next slide. So this is basically what you see when you load a model and try to print its architecture. I hope it's fairly visible to everyone. If not, I'll just increase the size a bit, right? There we go. Okay, so these are the parameters of the model that we just saw over here, right? So if you can see, there's this convolutional layer. There are 8 convolutional layers inside, 8 or 9 convolutional layers over here, and all of them have weights and biases. So this is the convolutional layer 1, and so on, right? These are the classification layers, which is over here, right? So this is essentially what a model is. A model is the structure of the model, which is the code, and the weights that you load into that structure. Okay, so structure, which is code, and you load weights, right? So this total is a model, right? Now, next we will look at the runtime stack. So what runs these models, right? In the runtime stack, there are a bunch of layers that we will traverse, but in the opposite direction that we have listed over here, right? So we'll first look at GPUs or FPGAs or any kind of specialized hardware, right? Then we will look at the driver and compilation layer. After that, we will look at libraries. And finally, we look at frameworks, right? So this is how essentially we will traverse this path. We will go from hardware up to high-level frameworks. Cool. I'm sure a lot of you have seen a lot of these things on LinkedIn or in a lot of other places. A lot of hardware hype going on as well, right? So I'm sure that all of you are familiar with NVIDIA CUDA. Especially gamers would be very much familiar with CUDA as well as ROCm. These are also the technologies which power a lot of gaming engines, right? Apple Metal is a new kid on the block, which works on all Apple GPUs. This was originally designed again for graphics processing and gaming, but turns out that that is the exact hardware that also runs AI, right? Now, AMD is a bit sort of confused in this scene. So, AMD actually has 3 technologies that do more or less the same thing, but maybe in a slightly different way, right? So, you have ROCm, which is majorly available on consumer graphics cards, right? You have RDNA and CDNA, which are majorly available on data center graphics cards, okay? The software stack of this is not yet very stable. This is the most stable software stack that exists, software as well as driver layer stack. This is also in development, right? Of course, we also have Grok, which I don't know, I've never laid my hands on any code that actually interfaces with Grok, so this is all under the wraps. Then we have TPUs from Google. We have Azure. I don't know what this processor is actually called. Maybe it's Maya. Then we have Inferentia from AWS, right? So a lot of new hardware which is coming out all across the board. Now remember, every time a new piece of hardware comes out, these hardware manufacturers will have a different set of APIs, or what we rather call it as instruction sets that they will create for these different kinds of hardware. Now it doesn't stop over there, right? So once you are a hardware manufacturer, and if you have built some custom hardware, you also need to provide a software layer support for that hardware. Okay. So now, next, so again, all these are just names of hardware technologies. Next, we will look at the software layer that actually makes these technologies run and provide an interface for building applications on top of that. So, for example, if you are a PyTorch developer, this is the area that you would be generally working on, right? Okay, so let's move on. So what is the crucial difference? Why do we need specialized software for a GPU versus a CPU? So this is this is a slide to show you guys like the basic architectural difference of how a CPU operates and how a GPU operates, right? So in a CPU, we might be familiar that we have multiple cores of CPUs. So these are large dies, core 0, core 1, core 2, core 3. Then we have L1 and L2 caches per core, okay? And then we have the L3 cache. L3 cache is shared by all cores, okay? So what happens really when you run a program is that your code and data is loaded from main memory into L3 cache. And then let's suppose this is the code that is processing your code, then it will be loaded from the L3 cache into the L2 cache, L2 and L1 caches, right? This entire process of data and code prefetch, right, is automatic. Okay, you as a programmer do not exactly have much control over this process. Okay, so the programming model of a CPU is linear, right? You have one linear thread, or even if you have multiple threads, you can schedule those threads, but they are all guaranteed to run linearly. Okay, that's how you write the code.
Lucy, I'm really sorry to cut you short. Actually, your voice is still echoing. At times, it's becoming a little blurred for us to hear you. So if you can try moving a bit away from the mic, I think that will help us out.
Away from the mic? Okay, sure.
A bit away.
I'm about a feet away now.
Yeah, I think that's better now.
That's better? Okay. I hope this is better. I've actually moved the mic a bit farther.
Yeah, it is.
Okay. Okay. So this is basically what the architecture of a CPU looks like, right? So it is actually very, very simple. There is a few number of CPU cores which are fairly independent, but they operate on some shared memory, which is also handled transparently, right? So the programming model of a CPU is linear. Now, things change in a GPU, right? What changes? Now, in CPUs, we have large cores which can support a much complex set of instructions, assembly language instructions, right? Which makes it possible for you to write more complex applications with very complex logic. So this is much more general purpose. It can solve arbitrary logic. In a GPU, you have much smaller cores. These are called as, for example, CUDA cores. Right? You have much smaller cores. They are not exactly specialized to be very independent from each other. Right? So, for example, in this red block, as we see, let's suppose there are 128 CUDA cores inside these. All of these cores have to run the exact same code at the same time. You cannot have one core running code 1 and another code running code 2, and so on, like you can do in a CPU, right? There are these kind of restrictions on a GPU. Again, there are 128 cores inside this red block. This red block is what is called as a streaming microprocessor, right? SM. Now, in my GPU, which is a 4090, there are around 114 SMs, making it a total of 128 into 114, which comes up to around 16,000 cores, processor cores, right? So we're comparing, let's say, maybe 8 cores versus 16,000 cores, right? Because of this fundamental architectural difference, the way you write software for a GPU is very, very different from how you write software for a CPU. Okay? So, generally, a software for a GPU looks more like a C++ program with special functions. Okay? These special functions are also called as kernel. Okay? So, if you look at deep learning, if you look at any, anything inside PyTorch or any other library that you know of, most probably they have one or a few number of customized kernels that they use to run your model. What a customized kernel means is that it's a custom piece of code that has been written to specifically run on a GPU. Okay, that's what a kernel means. Now, of course, when you're writing kernels is very, very tough. It's as tough as writing shaders for GPUs. By the way, if you have done shader programming, and a lot of the technologies that are used for shaders are also used over here. We'll go on to the next slide, which talks about things. So the computational model is. Let's talk about that as well. So the model that we saw over here, right, where you have each core running a small piece of code, but that piece of code is duplicated across, let's say, 16,000 times, right? This model of programming is what is called as single instruction multiple threads. Okay, so that is the paradigm of programming in which GPUs operate in. Okay, CPUs also have some specialized vector instructions which are called as single instruction multiple data. So something like if you want to sum, right, you can sum one number with another number and give a third number, let's say, in a normal instruction. In a SIMD instruction, you can sum an array of numbers with another array of numbers and get an array of numbers all in the same instruction and single CPU cycle. Okay, so just like sum instruction does only one sum, a vector sum instruction does sum on two vectors. Okay, so this is basically much faster than this, right? These are part of specialized instruction sets. So, for example, Intel has its instruction set called AVX, right? There's also SSE 2 and 3, right? So, these are essentially specialized instructions which are implemented by CPUs, right? And then specialized threading is what is implemented by GPUs. Okay? Now, what we had talked about is the very basics of the computational model. These are all the libraries that are built on top of that, utilizing that computational model to build various abstractions. Okay. So, for example, there are a certain kind of libraries that are called as BLAS. Okay. BLAS means basic linear algebra subprograms. Okay. So what a BLAS library does is, BLAS library generally has three levels: L1, L2, L3. Okay. L1 is more like, let's say I have a vector x, I want to multiply a constant with that vector x, right? So this function is implemented in L1 BLAS. Okay. If I have a matrix X and I want to do a with a matrix Y, okay, the implementation of this inside CUDA is in QBLAS. Okay, QBLAS is okay, QBLAS, right? Similarly, matrix multiplication using ROCm hardware and its architecture is implemented in ROCm BLAS. You know, OpenCL, Vulkan, Per, and SYCL, these are actually part of something called as Khronos group. Okay, so Khronos group is the group which is like a standards group. Okay, so they determine standards like DirectX 9, DirectX 10. If you play Counter Strike, for example, right? So those games and their shaders are written in specific languages. Those are called as shader languages. So GLSL is a shader language. HLSL is another shader language. HLSL is what you generally call as DirectX. Okay, GLSL is what you call as OpenGL. So you can run Counter Strike in OpenGL as well as DirectX, by the way, right? So these are part of. So these actually compile to something called as SPER. SPER is like the bytecode. So SPER V is actually the bytecode. Then this can either be run by Vulkan. If you are developing a game, then you would probably want to render stuff. This can also be run using OpenCL. OpenCL runs on CUDA, right? So essentially what I'm saying is, you can take the hardware also, which is responsible for graphics programming, pure graphics programming, and you can also use that to write kernels. Okay, so you can use CUDA to write kernels. You can also use Vulkan to write kernels. Okay, and this is the middleware layer of it. In fact, you can also use, if you are aware of gaming again, like there's this thing called as ray tracing. If you have played all the latest games like uh, Cyberpunk has like a very good ray tracing implementation. The ray tracing hardware and as well as a driver and software layer. Is my voice still unclear, by the way? Anyone?
It is clear now.
Clear now, right? Okay. So as I was saying, the ray tracing hardware can also be used to do matrix multiplication and matrix operation. Okay. So if you know deep learning is basically a bunch of tensor operations. By tensors, we mean matrices, right? So this is the middleware layer that, for example, PyTorch or TensorFlow uses in order to implement different parts of a neural network. For example, a layer might consist of a dot product followed by a sum of two matrices, right? So the dot product is actually part of L2 of BLAS. The sum is part of L1 of BLAS. So if I was implementing PyTorch, I would take like ROC BLAS L2 ka function, and then I will take L3 ka function. I will call those functions. That's how I implement a deep learning layer. Okay. By the way, it's okay if you don't understand anything over here, right? Just follow that there are these technologies, and each of these slides is a different career path, right? So if you are looking for a job in, say, AMD, right, for building the middleware layer for AMD graphics cards, then this is the stack that you would be working on. Okay. Also, if you are in a larger company doing fine tuning or training of models, again, this is the stack that you will be spending most of your time on. Okay. Okay, we have more libraries, right? So these libraries implement mostly linear algebra. Okay, so let me also show you some library essentially. I think I have okay. LC Blast. So, for example, if you can see this code, you can also go to library, RC, and you will see all the implementations. So, for example, level 1, level 2, level 3 implementations, right? Similarly, if you go to QBLAS, you will again see level 1, level 2, and level 3 implementation. So, for example, argmax, argmin, argsum, these are all matrix operations. They are all implemented over here. So Cuba Library Samples is basically a GitHub repo, by the way, and so is ROC Blast. You will also, so once I share these slides, you will find all of these as links over here. So you can just click on these links and it will take you to the site. Okay. Now, more libraries, right? So on top of these linear algebra functions, you can now implement entire layers. So what NVIDIA has done, for example, is that it has built cuDNN, right? So cuDNN is more like okay, I can't get out of the screen. Okay, so cuDNN is more like a bunch of libraries implemented, bunch of layers implemented. Right, so if you look at cuDNN docs, you will find something like this. So for example, this is the convolutional neural networks ka implementations. So as you can see, convolutional backward with bias, convolutional backward with data, with filter, bias activation, blah, blah, blah. So these are essentially parts of the of one convolutional layer. What is going on? Yeah. Cool. Similarly, we have flash attention. Flash attention has actually become very, very famous because it implements a part of the transformer network, which is common across all transformer models. And this is implemented in pure CUDA. So this is much faster and actually hand optimized, right? So this is again a special layer that you can apply to your model if your model has that kind of layer. The compute project. Compute project actually builds kernels out of a lot of this. Okay. So compute project is actually a project that runs on pretty much any graphics card that can do gaming, not just graphics card that supports CUDA. Okay. So this is, for example, the main project behind llama.cpp, right? So if you use llama.cpp, it's actually using a lot of these kernels from compute library in the backend in order to actually implement deep learning models. Okay. Similarly, you have DeepSpeed. Again, DeepSpeed is a very, very large project. One part of this project is customized kernels or deep learning layers. Okay. So these could be only one very small thin layer which does only one operation, or it could be a very large layer, like for example, an entire RNN layer, right? Or an entire transformer layer. So, these abstractions can be sort of arbitrarily complex, but those abstractions are implemented in these libraries. Okay, finally, we use all of this stuff, right? So we have CUDA, we have BLAS and other driver level libraries. Then we have higher libraries. So all of this is used to finally build deep learning frameworks. So this is PyTorch, by the way, and this is on NX runtime. Okay, so PyTorch is, by the way, extremely huge, right? If you look at PyTorch's architecture, you will find that there's a lower level. This level mostly deals with kernels. Okay. Then there's a higher level which provides an interface for dealing with these lower level stuff. This level also defines what a neural network is. For example, a module, layers and backpropagation. So for example, AutoGrad is the backpropagation part. A10 in PyTorch is the tensor processing library, and JIT is the just-in-time compiler. So you don't really have kernels written in PyTorch, you have kernel fragments written in PyTorch, and they are sort of assembled together by the JIT when you're running a model in PyTorch, right? Okay, you don't need to worry a lot about these things because they already happen. I mean, I'm sure that every one of us has used JITs without knowing what it does. But again, when you are optimizing, this is the exact stuff that you need to know, right? Okay, so this entire layer is exposed in the form of libtorch. Libtorch is a C++ library. Okay, so whenever you find torch in some other language, like for example torch in Java, that's basically Java which has integrated with libtorch. Torch in, I mean, for example, candle, torch in Rust, again, libtorch, integrated with Rust, and so on. PyTorch is basically libtorch integrated with Python. Okay, so you can actually, so when you have to do some deployment or run using Torch on production, you might want to use libtorch directly instead of using PyTorch, right? So you avoid the entire Python overhead, by doing that. Similarly, on NX runtime has a lot of computational graph stuff, that also exists in PyTorch, but it's sort of buried deep inside over here. There's a graph API from CUDA that is actually used by PyTorch, okay, as well as on NX runtime. On NX runtime is only useful for inference. It cannot be used to train a model. PyTorch is useful for a lot of different things, not just training, but also distributed training, which we'll talk about towards the end, right? So before we move on to operations, do you have any questions?
We do have a question in Q&A box. So the question says, are these blasts also specific to each type of GPU? CUDA versus AMD?
Yes. So as you saw, right? So again, as you saw, this is ROC BLAS, right? ROC BLAS is made specifically for AMD GPUs which support ROCm. Okay. MKL is actually the BLAS for Intel processors. Okay. Similarly, CL Blast is for OpenCL. Now, OpenCL can actually run on top of NVIDIA and AMD. Okay, so OpenCL is kind of generic BLAS. However, these are all specific to the hardware. By the way, NVIDIA QBLAS is not open source. Okay.
We also have Kushal who has raised hand, so I would request you to kindly post your question in the Q&A box and we'll take it up from there.
Cool. Then I'll move on. So, next we will talk about operations. Like how can we do stuff with these models, right? So we'll be talking about 4 parts, of course. We'll cover the easiest part first, which is storage. Then we will move on to inference. I suppose that in any practical scenario, 95% of you guys will be, if you ever do any kind of Gen AI, you will probably be doing inference, right? Maybe 5% of you will be doing fine tuning. This you require a lot of. So, okay, so we'll move on to storage. Now, the storage workflow for Gen AI is pretty much standard. Very similar to what you would be dealing with when you're dealing with any large artifact, right? So this part of the workflow is basically where data scientists work on these models, right? So you, as a data scientist, you might want to do different things with these models, but generally those things are limited to your own personal computer or maybe one server on AWS or whatever, right? So in these kinds of scenarios, you need to use a versioning system for your models. Now, Git is a horrible versioning system for models. Use LFS along with Git. But even then, Git is a very horrible way of managing GenAI models, because these models can be anywhere between 10 gigabyte to 200 gigabyte, right? So every commit that you do ends up being 200 GB. Okay. Hugging Face, for example, hosts all models in Git actually, but it does not make it very easy for you to clone it. If you try to clone Llama, you will actually end up cloning about 10 times of data than the actual size of Llama, because of all the history. Okay, so .git, for example, will be like 1 point something petabytes. Okay, so this is the workflow that you can use while you are developing on that model and working on the model itself, right? So build and push either into Hugging Face if you're a fan of it and if you're comfortable with the security, or into your own Git LFS, or into S3, or into some kind of an object storage, right? Object storage is the cheapest and the easiest. During development also, when you are doing, let's say, a lot of checkpointing, the amount of data that you store can blow up very, very easily, right? So again, a blob storage is sort of the ideal place to store everything. Okay. Then we talk about delivery. Now, while delivering these models, there are essentially two, let's say, not two, but multiple ways to deploy these. But we'll look at deployment a bit later. But delivering these models should always happen from a cloud storage. Never rely on Hugging Face, right? I mean, Hugging Face goes down arbitrarily, and they will also, cap your bandwidth. So you do not want to download like 200 GBs over 20 Mbps and while you're waiting for your service to get deployed. Instead, keep it in cloud storage, right? Sorry, object storage. Now, you can download the model, and you can either bake the model inside an image, or put the model inside a container and then deploy the container, or you can first deploy a pod and then pull the model when the service is up, right, and so on. So you can do multiple strategies from here. We'll talk about these strategies later. Okay. Cool. Now, one of the biggest questions that you'll get asked, like deploying a model, choosing an Amazon instance, and all of that stuff is not very hard. What is the hardest in this is figuring out what inference engine to use to run your model. Okay. Now, there are various categories of models. There are these big models, right? For example, which are backed by, let's say, Meta, Google, and so on, right? Then there are these small models also, which are again backed by larger companies. So, for example, T5 series of models, which will be one of those, right? Or let's say your audio models, like for example, OpenAI's Whisper, right? So Whisper models are all like sort of medium-sized 1 GB or less models, but they are supported by OpenAI. Okay. Then we have big models which are backed by community. So basically, some random guy on the internet has fine-tuned Llama 3 with like some random data set, and that is a famous model now, let's say, right? And then you have small models again which are backed by community. Again, same story. Like somebody has fine-tuned a model, that somebody might be famous or not famous, but nobody has really tested this model ever. Okay. So these, this section you probably need to first do testing, basic testing of the models, whether they even work or not, right? This part of the story, you have a lot of good tooling, right? Here you do not have tooling. I mean, Hugging Face is not tooling, by the way, right? Hugging Face is more like research convenience. But when you're looking at production, no Hugging Face. Like it's the worst possible thing to use. Okay. So here you have tooling, here you don't have tooling. So essentially, choice of model and its backers are, weigh a lot in your decision making. There are, of course, other engineering considerations that you need to do before you deploy any infrastructure. So one of those, I mean, the obvious consideration is how big is the model? Can I fit it inside one GPU? Right? Can I fit it inside 8 GPUs, which is the maximum amount of GPUs that I can have in one machine? Okay. Or do I need multiple machines to fit the model? Okay. Then we have batch sizes. So as we know, deep learning, you can either give it one input, get one output, or you can give it a batch of inputs and get a batch of outputs. When you batch, you get about 30 to 60% better performance. Okay. So pretty much everybody batches. Okay. The size of the batch determines, also affects the amount of RAM required, but also increases efficiency, but also increases latency, right? So it will obviously increase efficiency, but if you're chatting with this model, there will be some lag because the server will be waiting for filling the batch size. Only then it will give to the model. Something like you have an API, you have a buffer, and then you have model, right? So you call APIs, let's say 10 APIs have been called, then the model will be called with one batch. Okay. So this is basically how batching works. Then there are various optimizations that might also be done to the model itself. For example, if the model is quantized, you need your inference engine to support running of quantized models. Okay. Distillation, pruning. I mean, there are like 10 methods of quantization. Even I don't know what methods they are, frankly. Right? It's just that it decreases the model size and increases the performance. I mean, sure, if you want to read papers about it, you can. These are mostly, I mean, the logic is mostly based on matrix factorization, but sure, right? So whatever method the model has been optimized with, the inference engine needs to support running such a kind of model. Okay. There is caching also. So this is more like KV, key value type caching, which is done inside the model layers. So if in a model you have multiple layers, so instead of passing all data from one layer to the another all the time, you can also cache data from here. Okay, and then see if the data already exists in cache. If it exists, then just pass it on. This is a large performance optimization. But the size of the cache will also determine how big a GPU you need and how many GPUs you need. Whether you can do caching on CPU while running the model on GPU. So there are a lot of considerations over there as well, right? If your model a mixture of experts, so if your model is a mixture of experts, you have this kind of an architecture, right? So you have a routing layer, and you have various models over here, and the routing layer routes between different models. Now, an MOE architecture can be very large. You can either try to fit the whole thing inside one GPU, or you can fit these models inside each of their own GPUs. Okay, so there are various distribution strategies related to a mixture of experts model. Okay, specifically around routing. Okay, there's also LoRa. So LoRa's are essentially, I have a model, which does some task A. I want it to do task B. So I will add another layer and I will train it on task B ka data so that only this new layer gets trained. The rest of the model is the same. This new layer is called as a LoRa. Okay, this exists both in vision models as well as in LLMs. Okay, so if your model has LoRa's, or if you have, so for example, GPT store is basically nothing but the base model GPT with LoRa's trained on all the data that you guys are uploading, right? So it has, if you want like dynamic LoRa loading, like if you have one LoRa per customer in your model and you want to like shuffle 100,000 LoRa's all the time, then you need a different kind of an inference engine, and so on, right? There's also things like speculative decoding, wherein you have a larger model and you have a smaller model. The smaller model tries to predict what the larger model does. Whenever the predictions are correct, the predictions happen very quickly. Large model takes long time, small model takes less time. Okay. So this also is a performance improver, right? Some inference engines support speculative decoding, some don't. Finally, we have tensor parallelism. So tensor parallelism is nothing but I have two GPUs, I have one model, I want to load half model in GPU 1, half model in GPU 2, and I want to parallelize. If I have input, I want to also give input to both of them and get output from both of them and then combine or something. Okay. So this is basically what is tensor parallelism. Now again, if I want my model to be massively parallelized across GPUs so that I can do inference faster, then I would probably also need tensor parallelism. Okay. Now, if we are looking at the most popular LLMs only, right, then we have these options for inference engines. Now, this entire part is enterprise. Okay, this is part of what is called as NVIDIA. I think NVIDIA AI Enterprise. Okay, and these are of course extremely complex. So I would rather suggest not to use them unless you are building an AI company wherein you are serving large number of different models, or you are part of an enterprise AI team, central enterprise AI team, where you are responsible for example, serving like 10 models inside the organization. Okay. So if you need to load balance between, Llama is popular today and, Mistral is popular tomorrow, I need to have more Mistral tomorrow, more Llama today. So those kinds of, load balancing if you need to do, then use the Triton inference server. Okay. If not, then you would be using one amongst all of these other. These are like single executables, right? So all of them have custom CUDA kernel implementations. Okay. So if you ask me which one is fastest, I don't have a clear answer. In fact, nobody has a clear answer, right? You could go with something like vLLM or Llama CPP, which are the most popular right now, right? So for example, Llama CPP supports Metal. So if you want to run a model inside your MacBook, you would probably use Llama CPP, right? vLLM is the fastest for CUDA. If you want to run a model on production on NVIDIA servers, you would probably use vLLM, right? LoRaX is pretty much the only one which can serve thousands of LoRa's at the same time and load balance between them, right? So if you want to serve a large number of LoRa's, this is the only choice that you have, right? TGI is horrible, but it runs a large number of models. Some of the models which are not even supported by these other guys. So if you find yourself in that kind of a situation, maybe you are left with using TGI, right? If you're using Whisper, for example, right, you also have Whisper.cpp. So obviously, for Whisper.cpp and Faster Whisper, both of them. So you can choose any one of them. So how to choose an inference system? First of all, you have your requirements, filter out these based on your requirements. Most likely, you will end up with 2 or 3 alternatives. But when you have to compare between those alternatives, there is no other way but to do performance testing. I know that sounds, bad, right? It's always better if somebody writes a nice blog with a nice table with all performance listed in it. But, in practice, if you want to actually go to production, you have to do performance testing. Because even if your performance is around 10% less, you will be burning $200 per machine per month extra. Okay. So, this is the architecture of these inference engines, right? If we look at the architecture of vLLM, right, we have a scheduler. So all the API calls go into the scheduler. Scheduler will, cache the API calls till it has a certain number of APIs in the cache, and then it will submit a job to the LLM batch. Okay. It also has a KV cache manager, which allocates blocks per GPU. Okay. So like we talked about over here, if we need caching, vLLM has a very good cache management system inside. Okay, this is Triton, NVIDIA's Triton, right? So Triton, okay, by the way, VLLM is a standalone system. It uses everything custom, like including the kernels that it uses to run these models. They are also hand optimized and custom. Okay, Triton is different. Triton is one abstraction layer above all of this, right? So Triton can use TensorRT, TensorFlow, OnNX, PyTorch. It can also use VLLM, by the way, as a runtime engine. Okay, it can also use llama.cpp as a runtime engine. And it can run different kinds of models at the same time in a large cluster of computers. Okay, it has a standard API set and gRPC. It has various Python clients and so on. It can plug into a lot of different backends or frameworks which support different kinds of models. So you can also have like Hugging Face or PyTorch backend run literally anything possible in deep learning. Okay, so like VLLM, it is only specialized for a certain number of LLMs. They are listed in the README, by the way. Okay, in Triton, they try to support everything. Okay, but this costs you $1 per hour per GPU. Of course, right? This is open source. Okay, if let's suppose we are not using LLMs, right? Let's suppose we are using something like Suno AI Bark. This is a this is a text to speech model, creates voice, right? Parakeet, again, text to speech. Seamless communication. Seamless communication is this wonderful project from Facebook that does speech, text, speech to speech, speech to text, text to speech, text to text. So it also does translation. So for example, when you can do text to text translation or text to speech translation or speech to speech translation and so on and so on, right? But there's no inference engine to run this. So, you have to use Facebook's original project in order to run these models. Similarly, you have Paddle OCR. OCRs are generally two models. They are not one model, right? So always prefer using the sponsored project for these kinds of specialized models, right? That is basically the message. Everything else, right? Let's suppose I want to run BERT. Is not supported anywhere, or some other model, right? Not supported anywhere. What do I do? Well, you have Hugging Face transformers, right? You can run anything in it. Though, the performance might not be great, but it's still, Hugging Face transformers give you almost the same performance that PyTorch gives you, right? You also have Torch Audio, Torch Vision, and Torch Text. All of these are again based on PyTorch. They are very similar to Hugging Face. Okay, so if you are looking for a transformer model, you would probably use transformers. If you're looking for something that is not a transformer, you would probably look at one of these, right? So, for example, if you're looking for VGGNet, you would probably look at PyTorch Vision and not Hugging Face. But if you're looking for, let's say, Llama 2, right, you'd probably look at transformers and not any of these. Okay. There's also Google Flags. But to tell you very frankly, I want to be all inclusive and all of that, but nobody uses this. Pretty much the entire ecosystem is based out of PyTorch, and rightly so. Frankly, there's an evolutionary history as to how these frameworks developed. For example, one of the things that you might have seen that I've mostly skipped is TensorFlow, right? So horrible framework, horrible API, frankly, to use. So nobody uses anymore. I think Google itself has moved to JAX and Flags. JAX is the AutoGrad engine or the automatic differentiation engine, and Flags is the neural network library built on top of JAX. Okay. So again, yeah, you'll be. As long as you stick to this, you should be fine. Okay. Enterprise, it's a different answer, right? If you're an enterprise like 20,000 engineers with some 100 teams and so on, you do not want to do all these kinds of like scrappy work. You want to have like a proper solution with like proper support from the people who are building these stacks and so on. So, for example, you would go with NVIDIA NIM, right? So NIM, this entire process that we are trying to do, right? Inference, which is basically hosting API microservices with models, right? This entire thing has already been done and packaged by NVIDIA. That packaged Docker containers are called NIM. Okay, so you don't have to do anything, just Docker, just deploy it in Kubernetes or whatever. You also have Amazon Bedrock, Azure, Vertex AI, and all of your standard cloud solutions, right, which you can also try as an enterprise. Okay, not to say a lot about enterprise. Okay, deployment pipeline. What does that look like? Okay, so you have two. So I've kind of tried to enumerate two different kinds of deployment, right? One is your standard GitOps pipeline, right? Wherein you have your code for your API microservice. Okay, this might just be one line, by the way. Just VLLM run this module. That's it, right? Dockerized, right? And delivered via, let's say, something like Argo into Kubernetes, right? Once you deploy the code will, on start, it will try to pull the model from your S3. Once it has pulled the model, it will start the service. Okay, so this is one kind of deployment, right? You have to also configure Kubernetes and install NVIDIA drivers. You probably need to do that for a specific namespace and also have a node group with GPU instances for that namespace only, right? You have certain software that helps you do exactly that, which is NVIDIA GPU operator or IOCN GPU operator. This is very initial. I've used this in 4 cloud environments. This works extremely well. So you can actually get the Kubernetes configuration part done in about a day, right? Not that difficult. Once you have done the configuration, you have a special namespace which only works on GPU instances, and you're done. You just set up your Argo CD pipeline, and your code gets deployed, models get pulled, and things auto scale, and everything works as expected. That's pretty much what the GitOps pipeline looks like. But there's a problem, right? The problem is, so as long as you're working with 1 or 2 instances and your scale is fairly low, right? For example, in like support use cases, for example, where you have like at max 5 people chatting at the same time, you probably don't need more than 2 instances. Okay, so in those kinds of cases where the number of instances remains stable and auto scaling has a large amount of latency, because this download will take time. So if your traffic increases, if Kubernetes scales up, even if it scales up and deploys like 10 servers, it will take like 10 minutes for those 10 servers to download that model from S3. Or if you also put that model inside a Docker container, it will take 10 minutes to download the Docker container from your registry into Kubernetes and so on. So auto scale is very, very, very slow in these cases. Okay. If you are building a low latency system in which you do not want that auto scale, to take so much time, then you probably need to do machine images, right? So you take the model and the code and bake it into a machine image. If you are from AWS, you bake it into an AMI, and then use that AMI to auto scale with a load balancer. In this case, in AWS, it will actually be an auto scaling group, right? Not really a load balancer, but sure. Right. So use a load balancer to spawn instances. Instance spawning is extremely fast, even if you have a large machine image with a large model inside that image. Okay. So over here, this system will be much more reactive to your traffic. Okay. I think I have finished this section. Yes. Any questions before we move on to the next section? What kind of what kind of testing would you advise for LLMs? So again, I'm an engineer, right? So I'm not going to test for, oh, did this LLM reply to my query right or wrong? The kind of testing is mostly I'm referring to is performance testing, right? So performance testing with your specific type of hardware on your specific GPU with your specific software using the specific kernels that that software is configured to use, because even that changes, like sometimes you have one kernel which like increases 10% efficiency and so on, right? So if you have different inference engines, let's say three candidate inference engines which you have identified, okay, these three look good, right? I would say that build a Docker container out of that, have spawn a machine in AWS and run these things for at least a few hours with, as much traffic as you can pump into it to figure out what the maximum throughput of the system is, what is the maximum batch size that you can go to without, doing a out of memory allocation on the GPU, stuff like that. How much can you stretch without like, completely breaking the system? That is the test that you need to do. Okay. Now, why am I saying this? Because again, LLMs. So, okay, there's a funda about GPUs. Okay, GPUs are very sort of can run only one model at the same time, one large model at the same time. Okay, so you cannot like load balance using a GPU. Okay, so even if 5 people are chatting, if you don't have batching, then this first person, if they are executing a query, the second person has to wait for that query to execute. You cannot do concurrent processing. Okay, there are like those kinds of restrictions in LLM. So you need to like do load testing on it. Anything else? Of course, I will not talk about quality testing because again, this is an engineering lecture, right? I'm not a product manager. Okay. Next we move on to fine tuning. Okay, things kind of get interesting over here because slowly we are moving into distributed systems, right? And whenever things become distributed, as you know, things become really complex. And this is a kind of distributed systems that I'm sure that you guys have maybe studied in college, but you have never exposed to. Okay, these are high performance clusters. So let's go into that, right? So fine tuning. While if you are trying to fine tune a model, so fine tuning a model could mean a lot of things. As usual, you can have BERT, right, which I can fine tune on my laptop. You can have, let's say, Llama 7B, right? Llama 7B fits in my 4090, my desktop GPU, right? I mean, actually I can, fine tune or train it even, right? Then you have something like a 30 billion B model, which will fit inside a 80 GB GPU. Then you have models which can fit into 4 cross 80 GB GPUs. Plus, you also have models which fit into 8 cross 80 GB GPUs, right? These are still, all of these are single instance. So you have one machine with multiple GPUs connected to that machine and you are trying to use that. If you have multiple machines, then that's a very different thing that we'll look at. Okay, cool. So things that are engineering considerations. One is size of the data set, right? If you are fine tuning or let's say, 1 GB or 10 GB of data, you are probably better off, using your desktop or like a EC2 instance, right? However, if you are working with 1 trillion tokens, then of course it's a very different story. You probably need to use Spark in order to process that data, pre-process that data, store it inside a specific file system, which is very high throughput, and so on. A lot of customizations you'll have to do. Size of the model, of course, right? As we saw in inference, if you have a 1 GB model, right? 1 GB model for inference. If you try to train it, right? Train the whole model, you would probably require around 3x the size of the model as GPU RAM. Okay. If you are fine tuning, but if you are like sort of quantized fine tuning. Let's say parameter efficient fine tuning. There's a Hugging Face library also called PEFT. Okay, so if you are using PEFT to fine tune, where you are not training the entire network, you are training some part of the network. So that some part of the network, a memory into 3 plus rest of model is what you need. Okay. Next will be obviously batch sizes. If you have if you have like 10,000 batch size, then obviously you are going to run out of memory. If you have 2 batch size, then your model will be like extremely slow. So you need to figure out the proper batch size so that performance is also there. But I mean, it's not the whole thing fits inside a GPU reasonably, right? Then you have parallelism. When you're fine tuning a model, if you have 1 trillion tokens to fine tune, it will take you 10 years to fine tune it on one machine. So you have better parallelize the whole training, right? Quantization, again, fine tuning becomes easier for quantized models, but you know what? Nobody cares about the performance loss. I mean, the quality loss of the model, right? If you pick up any the block model from Hugging Face, none of them are tested for quality, and they can range from okay to like, oh my god, this is totally horrible, right? And you're up to yourself, frankly. Summary routing, again, internal structure that we can exploit in order to optimize. Why not? Right. So these are the considerations that you'll be looking at while figuring out what to use in order to fine tune, what kind of an infrastructure to also deploy in order to fine tune, right? So fine tuning is generally a one-time task. You don't exactly need to do a lot of automation over here. However, for single GPUs, it's pretty easy. Just give your data scientist a machine and that's it, right? Can be used for up to 13 billion models, 80 GB RAM, or small models with relatively small data sets. If your model is quantized, or if you are training just a LoRa adapter, if you're not training the entire model, good idea to do one. If you have simpler tasks, so for example, if you're training just a classification model, right? Again, you can use a single GPU configuration, right? Just just an EC2 instance should be more than enough, because again, these are not exactly very repeatable activities. It's like a chunk of time you'll be doing fine tuning, maybe 30-40 times you'll be doing fine tuning over different models, and then select one model that works, and then maybe revisit it after 1 year, right? These are again expensive operations. So, if we need to fine tune on multiple machines or multiple GPUs, then we have to worry about the kind of parallelism that we are going to employ, right? There are various kinds of parallelism that are possible on GPUs. Okay, so single GPU, I'll not talk about that. Very simple, right? If you have, let's say, multiple GPUs, and if you have a model that fits inside one GPU, you can replicate that model across these GPUs. This is called as data parallelism. Generally, when you're training a model, if you're pre-training a model, this is like 1000 GPUs. So fine-tuning a model, this can be anywhere between 2 to 100 GPUs. Okay. So again, I can fit one model into one GPU, so I can, clone it and then train in parallel, right? If my model cannot fit in one GPU, then what do I do? When do I do tensor parallelism, right? Tensor parallelism means I break the model into 4 parts and put each part inside one GPU. And when I do a forward pass, I do a forward pass here. Okay. So finally, we have pipeline parallelism. Pipeline parallelism is my model is too big for one GPU. So while doing forward pass, you can also load one layer of the model, do the forward pass, and then again unload that layer. Load another layer of the model, do a forward pass, again unload that layer. Load third layer, forward pass, unload. Load fourth layer, forward pass, unload. Okay. So this is how I can take the advantage of the model's internal structure in order to, possibly fit that model into a GPU. Okay. This is like extreme poverty, by the way. Okay. Like if you are doing this, you are probably doing this in your local GPU. You are not doing this in production, right? I mean, this is like super extreme poverty, like, you know. Okay. So, then there is this is basically Sabka right? This is fully sharded data parallel. This is used by someone like OpenAI, whose models don't even fit 8 GPUs. Okay, or someone like Llama, like 200B that is being, sorry, 220B that is being trained, which again doesn't fit inside one server rack. It has to work across server racks. Okay, so in fully sharded, in FSDP, what you do is you take the model and you break it up into arbitrary chunks or shards. Okay, and you distribute the shards amongst different machines with GPUs. You compute, and then you have reducer machines, which again pull everything that is computed from here and then again push it back. So if you have heard of scatter gather algorithms, FSDP is essentially a scatter gather algorithm. So take a big model, you scatter that model into various shards and scatter it across a cluster. Then once you're done with like one pass, then you again gather all of those shards and make it a whole model. And then once you have updated the weights, you again scatter it. Okay. So that is basically what is happening in FSDP. This is standard data parallel training. As you can see, one model per GPU. We do a forward pass, we do a backward pass. Then we sync all the gradients across all of the different instances of the model, because otherwise the gradients will be all different. All models will have different weights, right? So we have to synchronize them, average them, and then again distribute them across the models, and then we finally update their weights. Okay, this ensures that we train effectively only one model. We don't train like 10,000 different models. Okay. Tools, right? You can obviously use PyTorch directly, right? So PyTorch actually has, or it doesn't have, something called as a trainer. This is generally a class that you write and you pass your model into the trainer, and the trainer takes care of training your model. Okay. If you're if you're trying to do fine tuning in PyTorch, most likely you are the one who is writing this trainer class. If you're using, say, PyTorch Ignite or TRL or TEF or Colotl, PyTorch Lightning, and Colossal AI. Okay, so if you're using any of these guys have a custom trainer implemented, so you don't really have to do much. Okay, these are sorry, not this, sorry. This and this are also support distributed training. So for example, in all of these repositories, you will see pipeline parallelism to data parallelism to tensor parallelism ratios. Okay, so when you're training a model, you have to determine, oh, I have a model that fits inside 2 GPUs. So my tensor parallelism is 2. I want to have 100 instances of this model. So that data parallelism is 100. Of course, I am not clear. So this pipeline parallelism is 1. Okay, so you also find these numbers on trained models, which are trained using these trainers. There are also like these, high-level training libraries. Like for example, XTuner is used for tuning InternLM, by the way, which you can find on Hugging Face. You can use these for like single machine use cases, right? Okay. Next, we'll move on to pre-train, but before we do we have any questions for fine-tuning? If not, then I will continue. So, according to me, this is the most important, most interesting part. It also, as you can see, burns a lot of money, right? But of course, that's why it's interesting. So, the interesting parts are essentially that, okay, so first of all, pre-training, continual pre-training, and, full network vanilla fine-tuning is essentially the same thing. Okay, so don't get confused over there. it just, so if Meta trains a model for the first time, they will call it pre-training. If you take their model and like continue to train that model like they have trained that model, then that is called as continual pre-training. If you use your own data to sort of train the model for a different task, that is called as fine-tuning. But from an engineering perspective, all of these are the same thing. Okay. Now, train the whole network. That is basically what we mean. So no LoRa's, right? Generally, you have large amounts of data, and generally you also need large amounts of compute. Okay. In a distributed case, generally you are dealing with thousands of GPUs. So in that case, you will not find all GPUs to be NVIDIA. You will have an assortment of GPUs. So you need to figure out how do you distribute, right? You will have one, let's say, bunch of machines which will run AMD. You will have, let's say most of your other cluster will be on NVIDIA, right? So you'll have to have the base layer of driver management done separately for each of these parts of clusters, right? You also have to figure out this ratio. For example, data parallelism, tensor parallelism, pipeline parallelism ratio. If your model fits inside 8 GPUs over here, and these 8 GPUs generally have interconnects, so they are highly connected inside one system, so they can also talk to each other very fast, right? Compared to this GPU trying to talk to this GPU. Okay, they can also do that, by the way. There are special networks that specifically connect GPUs inside a entire data center. They are also called as infinity fabrics. I will not go into that because that is like data center engineering. Okay. Anyway, so yeah, these GPUs are highly connected. So I can say that, oh, if my model fits inside 8 GPUs, I can use this. Then I can multiply it by, let's say, 100. So I have 800 GPUs inside 100 nodes. Okay. I might also need some special reduction servers, as we talked about before, while doing this. So during the reduction operation, you might want the entire operation to be done by a specific set of servers. They are called as reduction servers. So again, like if you are actually spawning this kind of a cluster on GCP, it's just a button, oh, I want to have reduction servers. But there is a theory behind it. It makes things much faster. It makes, especially this step, wherein the entire cluster communicates at the same time. This step becomes like really, really fast if you have these reduction servers. Yeah. High performance clusters. Finally, this entire thing is basically a high performance cluster. What does a high performance cluster look like? Okay. Kind of like Spark, but not exactly like Spark, right? If you have done Spark. Okay. So high performance clusters has a head node. Head node has something called a Slurm. Slurm is basically a job manager. If you have used something like Airflow, Airflow is sort of the job manager, right? So Slurm is the HPC equivalent of job manager. I'm giving a very bad example, by the way, but sure. Then you have machines, EC2 instances, which are managed inside a private subnet. Again, you can have different kinds of EC2 instances, or you can have just one kind of EC2 instance. Both should be fine. Okay. You have a specialized file system called Lustre. Okay. So Lustre is a file system which has its own cluster actually. And this is one of those file systems which is, there's also GlusterFS and Ceph, by the way, as alternatives. Okay? So these are specialized file systems which are used, for example, for implementing something like S3. Okay. Very, very high throughput, very, very low latency. They can also support, certain kinds of network protocols. So, for example, there's a network protocol called InfiniBand, or rather a network fabric called InfiniBand. which it can support. So again, InfiniBand is basically one of those networks which is like low latency, like less than 1 nanosecond latency network, right? So this is like Super Ethernet. Okay, but you can actually have graphics cards communicate with graphics cards over this, well, I don't know, Super Ethernet. Okay. So again, if you're a DevOps, you'd probably be interested in Azure HPC, Parallel Cluster, all perform HPC tools, and this is again a Parallel Cluster demo, by the way. So AWS Parallel Cluster is the best tool to deploy a HPC cluster inside AWS. Of course, we have Lustre, we have Slurm, like I already talked about. We also have OpenMPI. Some of you might have read about this in college. Okay, this is more of a threading library. Okay, generally used, mostly used exclusively in HPCs. I mean, in fact, if you have also seen Karpathy's recent code base, right? He also uses OpenMPI, by the way. So, and everybody from OpenAI to Meta, etc. Literally everyone uses OpenMPI for their training, for distributed training purposes, right? You have NVIDIA Pixis. Pixis is like a plugin over Slurm. It manages some NVIDIA hardware stuff while you provision instances inside the cluster. You have Horoward. Horoward is more like again, it's a library for FSDP, makes parallel training possible. So it actually has multiple threads through which it does data delivery to a model. Now, again, a GPU is mostly a compute infrastructure. Most of the bottlenecks of a GPU is not exactly in compute; it's actually in data transfer. Okay, so most of the software over here are like data orchestration libraries, which help in training GPUs in multiple machines and so on, or multiple GPUs, right? You also have Colossal AI and Megatron LM. So these are the template projects which most of academia as well as most of the people who are training large models from scratch, they use. Okay, so if you want to let's say train a Llama kind of a model from scratch on like 10,000 GPUs and so on, you would probably deploy NVIDIA Megatron inside let's say AWS using AWS Parallel Cluster. This is one of the demos for it. Okay. And inside it, of course, you would be running Torch in order to train the models, right? So yeah, that's pretty much it. Let me also show you guys some code if I can minimize this. Okay. Yeah. So let me. Sorry. If you want to check out some of this code, I mean, I think please. So Llama Recipes actually has a lot of this stuff, but sort of code that is thrown into a repository, right? So let's check out config. So as you can see, this is a Slurm file, right? In fine tuning, you'll actually find fine tuning examples for single GPU, a multi GPU, which is all possible inside one machine. But once you go into even two machines, you require Slurm and an entire HPC and so on. So, for example, they're using Torch-Run in order to run the model with FSDP and PEFT. PEFT method is being used as LoRa, and you have the the server backend head node over here, and so on. So a lot of examples you can actually find inside this repository. It's a very, very good repository, right? A lot of internal scripts and stuff that Facebook has been using, they have been throwing those things at this repo. Right? Do I need? Okay, I'll also show you guys like a little bit of CUDA, maybe. Okay, so this is essentially some C++ code which just adds two vectors. Okay, so very basic code just to show you guys what CUDA programming looks like. Okay, so this is just a C++ file, right? I mean, there's nothing out of whatever about this file, except for this one function, right, which has a global in front of it. So this is basically what a kernel looks like. Okay, it's just a C++ function, by the way. It's just a specialized C++ function which is written in a specialized way, which does only computation. Okay, and then you can call that CUDA kernel from your C code. Okay, where you also supply all the data to it, and you define how many of these cells. How many of these CUDA cores do you want to use? That is essentially this entire thing. Okay, so that's pretty much how you run a CUDA, But of course, it gets sort of advanced really quick, right? So you have this. This is more of a more proper CUDA kernel. As you can see, CUDA kernels generally are very small slices of code, but they are hyper optimized. Of course, if you're writing using C code, again using OpenMPI, this is the extra code, for example, that you need to write now to parallelize. So, for example, this for loop actually executes in parallel because we have specified this. That's all. That's the only difference between like normal C code and using something like OpenMPI. Yeah, guys, that's all. Questions? Oh, also, I think I covered too much in today's lectures, right? So lecture or whatever. But the thing is, a lot of you, I find that the amount of things that you don't know is large, and probably a lot of these things are some things that you guys probably even have not even heard of, especially the hardware layers and so on. If we move on top of this, most of the things are very famous, so that's why I chose not to explain stuff like LangChain. Okay, because those are like just application libraries. That's it. I'm done. I mean, if you have any questions, feel free to ask.
To all the participants, please feel free to drop your questions in the Q&A and we'll take it up from there. Yeah, we do have a question here. Can we get to use the use cases and industry examples to explore further?
Use cases and get to use the use cases and industry examples.
Can we get to the use cases and industry examples to explore further?
Exactly. So, like I said earlier, right? I mean, one of the things that I'm not talking about is use cases for LLMs because it's product. I'm not here to talk about product. This is an engineering lecture, right? So, I don't care which LLM we are talking about. I mostly care about how to optimize that based on its structure and not on its quality of functionality. That is not my problem, right? If you ask me like which model is the best, like human level for question answering, I don't know, frankly. We need to find out. Yes, so career insights, right? I mean, if you look at pretty much all of these slides with a lot of stack sort of populated in these slides, each of these slides is like a career path. Okay, so for example, this slide that we are looking at, if you are a hardware engineer, right, or if you are a driver engineer, you are working with AMD or NVIDIA, then this is the thing that you will be working on, right? Similarly, if we go towards okay, if you are working in, let's say, some kind of in Meta or in Google and so on, where you're working at the framework layer, then these are the things that you guys will be working on. Or if you're working, for example, in Qualcomm, on like mobile devices and so on, mobile like middleware layers, or Android, again, these are the libraries that you will be working on, right? Frameworks, if you are a data scientist, obviously this is your bread and butter, right? You will be authoring the model, running the model in local, testing, and so on using these frameworks. If you are a operations and engineering person, these frameworks will also tell you what all to optimize in the actual, stack that you'll be using to run these models. Okay? Because again, most of them, stacks are also derived from these frameworks. Okay? These frameworks are huge, by the way, right? If you look at, all of these inference operations that I was talking about, right? This is what most of you will be doing, right? So the career options over here are like ML engineers. So most ML engineers will be working on inference operations, right? Most ML engineers will be figuring out how to optimize the performance, the runtime performance of a certain model, right? How to decrease the cost of the model, and so on. Those are the primary considerations of engineering. Um, Okay, again, if you are working in an AI startup which is building these, you will be directly working with, directly building these kinds of inference engines. If you are working in any startup or any enterprise which is using models, then you will be directly managing these inference engines, right? So it kind of goes for all of these inference. If you are doing so this is mostly the DevOps part of LLMs, right? So if you are strictly a DevOps engineer, then you will at least need to configure the hardware. Okay. So for example, bringing up a Kubernetes cluster with GPUs, or having machine images which are specifically built for GPUs. Again, you have to add from the operating system, install various drivers, and these are kernel drivers, restart the system, load the driver, and then create an image. I mean, there's a long process of doing these, right? Also, drivers change, CUDA changes. Sometimes, things are not compatible across versions, and a lot of other nuances. Those are the things that you guys will be dealing with mostly in this. Fine tuning. Fine tuning, the major niche that people develop is clusters, high performance clusters. Again, this is something that traditionally has been used for stuff like climate modeling, right? If I want to simulate the gravitational fields of the solar system up to 1 millimeter scale, this is the kind of cluster that I would use, not a Spark cluster, right? And so on. So again, the expertise of these are generally with people doing PhDs and so on in computational sciences, right? And that's the kind of job roles that they also end up doing, mostly heavily computation, heavily algorithmic, right? And a huge number of distributed systems. Okay. So again, like you saw, these are just images, right? But if you go into these each of these projects, you will find that they have huge number of layers. Each layer has a lot of complexity, and each of those layers basically make up different job titles, in fact. Okay. So someone working on VLLM at the kernel layer is more or less a NVIDIA or a embedded systems or hardware type engineer. Someone who is more or less working on the the interface, network interface layer, they are more of an application engineer, and so on. So these are like teams of 100, 200 people, right? Which have different career paths. If you go on to pre-train, these are mostly either scientists or HPC engineers. So if you go to LinkedIn and if you search for HPC engineers, you will actually find that everyone from Hugging Face to all of these bigger AI startups, they all have HPC engineer requirements, and the job title is itself called as HPC engineers. These are the kinds of stuff that you will be dealing with in that career path. Okay, so again, each of these slides is like a career path.
So, thank you so much, Rusi. And we really hope that this webinar has sparked your interest in the vast potential of this field. But how can you take this knowledge and take it and turn it into a real world advantage? I would suggest consider taking our IIT Mandi certificate program in applied AI and machine learning. This 6-month program will offer you 120 hours of live sessions by IIT Mandi experts, comprehensive curriculum from Python to AI for speech processing and computer vision. You will also get to work on hands-on project, case studies, assignments, and you will also get to have an experience of 5-day campus immersion at IIT Mandi campus, where you will have the opportunity to network with your peers, with your faculties. And upon completion, you will also be getting a certificate of completion that will actually help you enhance your resume. So I would drop the link into the chat box so that you can go and explore the program. So thank you so much. Thank you so much, Rusi, for this engaging webinar and to all the participants who joined and took part in this. So we really look forward to exploring the future of technology with you in the upcoming session. So do stay tuned for all the upcoming webinars.